So we've been studying stoichiometry. Stoichiometry is basically you take the balanced chemical equation. That's like a recipe. If you have to imagine, as we said last time, that there is a box of irons with irons in it, and there's a box of oxygens with oxygen molecules in it. You take 4 irons out of this box, you take 3 oxygens out of this box, you take them apart, and you put one thing into this box. That's what the coefficients told us. We spent some time last time saying, well, if you had 0.1 moles of iron and 0.1 moles of oxygen, well, since the iron is used up faster, this pile would run out, and we would stop making the iron 3 oxide when the pile was empty. So how can this be different? Well, it can't. All stoichiometry problems are the same thing. So how can they look different? Well, we could start by saying, instead of how many moles of each starting or reactant, we could say how many grams. Let's say you had 10 grams of iron and 10 grams of oxygen. Now I cannot do 4 grams of iron is 3 grams of oxygen. That's not how it works. We have to use counting numbers. So we have learned how to change the grams of iron into moles. So let's see, if I do 10 grams of iron, and I know that it takes 55.847 grams of iron to have a mole of iron, then I can say that 55.847, that there is 0.179 moles of iron in the original iron bucket. If I have 10 grams of oxygen, now oxygen's a molecule, so I have to say there's 31.9988 grams of oxygen in a mole of oxygen molecules. Notice there's 1 mole is 31 grams. This 3 does not have anything to do with the determining how many moles of oxygen there are to start with. So if I have 10 grams and I have 31.9988, there is 0.313 moles of oxygen when I start. Okay, so if you ignore all that and redo what we did yesterday, if I had given you this problem, 3 O2s makes Fe2O3, and I took these numbers and put them right here, 0.179 moles and 0.313 moles, which pile runs out first? Well, now it's easier to see, and it looks just like the problems we did yesterday. We have less iron to start with. It's being used up faster. I can prove that that pile runs out first. That many moles of iron. It looks like there's 4 moles of iron for 3 moles of O2. That would come out 0.179 times 3 divided by 4 comes out 0.134 moles of O2 needed. And if you have that many needed and you have 0.1313 in the bucket, clearly the iron runs out first. And so that means if that's the limiting reactant, we can just continue on like we did yesterday and say the 0.179 moles of iron and 4 moles of iron makes 1 mole of Fe2O3. If they asked for how many grams of that, there would be one additional step where you convert 1 mole of Fe2O3 to how many grams it is by looking up the periodic table. I'm hoping that you can see that when we started up here with what some teachers call a mass problem, I don't look at them that way. I look at stoichiometry as if you know how much the starting amounts you have, you can compare them to figure out which pile runs out first, and then use the pile that runs out first, which we call the limiting reactant, to determine how much product you'll make. All stoichiometry problems end up being this. Okay? So we don't have to have many different styles of stoichiometry. There's only one. You take the starting amount and you do a mole to mole ratio. So if you're given the starting amounts in grams, just do a small problem to convert them to moles, then pretend this doesn't even exist and turn the problem into a problem you're more familiar with. These are the problems we started with. Any time you're given grams, you can convert them to moles and then do the same logic we've been practicing the whole time. So we don't have to learn special kinds of stoichiometry. There really is only one kind.